Hello everyone, my name is Aidar, and in this video exercise 8 implementation of hydrological model part 3 I will show you how I calibrated Zarafshan river basin. If you've seen the model setup video, you will notice that I made few adjustments to the model. First, I increased the number of elevation bands from 9 to 10. It's easy to change in the R here. In the HRU delineation chapter, you just need to change 9 and then run the whole script again. Additionally, the precipitation forcing data has been rescaled to improve accuracy based on updated data. If you see in the bias correction video, we've done it there because the Chelsea data overestimated the precipitation data compared to measured lapse rates. Finally, I've removed the kinematic wave object to streamline the model and focus on key parameters. They are 10 HPV models. And this kinematic wave object had little impact in this specific case. The special interpolation is the Shepard method. Evapotranspiration data is calculated with Odin method. Next, as I said, we have 10 elevation bands and we have only one zone for the calibration. We can look at the parameters here and see we have only one zone and 10 elevation bands, and we can see every parameter for all 10 elevation bands. The model period is from 1981 till 2010. The simulation time step 1 day and recording time step 1 month. The initial conditions are on the December 2010. Let's click validation and start to see the calibrated model. Here is the calibrated model, and as we can see, the model metrics indicate a good fit between the simulated and observed data. For example, the Nash-Sutcliffe efficiency Nash is 0.86, which suggests that the model is able to replicate the observed flow quite well. However, while these metrics are encouraging, there are some areas that need closer look. For example, the relative root mean square error RRMSE is 0.34, which indicates that while the errors are not excessive, they are still significant enough to warrant attention. This suggests that there might be some inconsistencies in how well the model is capturing certain aspects of the flow dynamics. The normalized peak error is slightly negative, which implies that the model might be slightly underestimating the peak flows, which we can see on the calibration period of the model. And this metric can be critical depending on the context of the study. For example, if you do flood risk assessment, then these peak errors would be super important. And while the model is generally good, further refinement may be necessary, especially if accurate peak flow simulation is critical for this. In the previous video, I walked you through the general process of calibration in a hydrological model. Today, I will show how I did the calibration for Zarafshan River Basin. As I mentioned previously, you need to start from simple to complex. You need to do everything step by step. First of all, I exported the initial parameters without any calibration, and then I started the calibration with only one indicator for objective function with one zone, all elevation bands, and with a calibration period from 1981 till the 1999 with a recording time step 1 month and simulation time step 1 day. And first of all, I calibrated these three parameters: CF max, CFR, and CWH. I clicked start and waited till the results are ready. After the calibration is done, go to the model, change the solver period to the validation period from the 2000 till the 2010, and validate and start to compare results on the validation period. Remember that in the calibration period you only calibrate and you check results on the validation period. And if you want, you can open the whole period to check and compare results to the previous uncalibrated one. And if you are satisfied with these results of the first run, you need to export the parameters and call it, for example, first run, something like that. And somewhere, for example, in the notepad, you need to write that the first run of your model was the CF max, CFR, and CWH. Also, it would be good if you wrote the results matrix, for example, the Nash value. For example, like that. You can do it differently. Most importantly, it should be understandable to you. Then I go to the second run of the TT, TT-int, and TT-SM. Then I click run, and after the run is complete, and after I check the values again, I save them and write in the notepad the results and what I calibrated. Third calibration is the beta, FC, PVP, and Sumax. I calibrated the same way, I check it the same way with the validation period. If I am satisfied with the results, I export the parameters with the name 3 because it's my third run, and then I write in the document what I calibrated and what is the Nash, and maybe some different comments. After that, I change to calibrate KR, KU, KL, and KPEC. I start the calibration, wait several minutes, then when I have the results, I validate and start the model to check in the comparator what the validation period, and I also check the best and current solutions graphics, and I export the parameters in the first run. Then I made a note that I calibrated the first time. If the first round of 4 calibration runs didn't get you good results, then you can start doing the same calibration with the same 4 runs, but instead of IV from model and defined initial values, you need to do the random IVs. After you do that, you can check the results. I did that, and in my case, the random initial values performed much better than the initial values from model in this Zarafshan river basin. Next, I noticed that parameter CF max was way too low for the 10th elevation band, so I manually changed it to the 17. And if we look at all parameters for all objects, they are the same, except the A parameter, which is surface of the elevation band and the CF max. And again, don't forget to export parameters after each calibration run. It will save your time and it will save you in case if some calibration runs would destroy your work, so you can easily import latest best parameters. And you can also try different indicators for objective function. For me, for this case, the Nash Pearson correlation coefficient, root mean square error, and normalized peak error performed better than other indicators. In the end, you can calibrate the model like me or even better, so the result, something like this, can be acceptable, and then we can use this kind of model in the next video. That's all for this video. It was exercise 8 part 3. If you have any questions, you can write us via email or down in the comments. See you in the next video.